So anyway, now we're going to transition into, I think, the star of the show, which is R. So I'm going to start off with just a really high level overview about R. I'm doing this because I'm not sure where everybody's coming from with R. So I'm going to take the perspective of, I'm going to describe to you what even is R, and I will go through syntax that shows you how to do some of the basic things in R today. So R is a statistical programming language released in 1993. It's actually similar to S, which is just funny how R came after S, but S was released in 1976. And so there's the link to download R. We'll go into all the syntax specifics in just a bit. What I also have on this slide is RStudio. So I want to take a minute to pause and describe how they work together. So you can download RStudio, but without a version of R installed on your machine, all you have is an interface. You don't have anything that you can do anything with. And so this complement of RStudio and R allows you to have a graphical user interface to do things in R that would previously be only possible with code. So it makes it easier to see where your plots are, or edit things in the files, or change some settings. It's now with a GUI versus doing everything in code. So I find that it's very accessible for folks that haven't done a lot of programming before, because there is a button counterpart for most actions in RStudio. So this is my workflow. I don't do anything like in R directly, or almost nothing in R directly. I work almost entirely in RStudio. There's a couple things that I actually do in R, which is generating the textbook for this workshop. So there is an R syntax to generate what's called the book down book. And so that's one of the only things I do purely in R. Otherwise, I'm in RStudio for a lot of that action. Now, one of the things that's going to become really important for you to learn as you're learning R is, in general, what are R packages, and then which ones you should be thinking of using. So in general, I like to think and compare R packages to like the App Store, where there's just like a bunch of apps out there and you grab what you need or don't need. And so they're essentially libraries of code to accomplish very specific functions. So you might find that there's a dozen data visualization libraries or packages, probably 24 machine learning packages nowadays, a couple really good data wrangling packages, and packages that do very specific things like computing effect sizes or reliability. And so you can publish R packages to GitHub. And so I do a lot of that now, specifically internally to like work with Gabby and other students. I also can publish R packages to CRAN, which is like the centralized repository. That really is almost like the App Store. When you put something on CRAN, it has a review process. Like someone somewhere is actually reviewing your code, as well as software processes that check that the code actually runs. And so CRAN is a place where you can host your packages, but it's not necessarily simple. Like there's a lot of learning that needs to happen if you want to get something on CRAN. And as I mentioned, you can also install packages via GitHub. So if you run these 2 lines of code, you'll actually install a package that I created a couple of years ago called RUF, Random Useful Functions. I couldn't think of another name for it because it was just a hodgepodge of things that I needed on a daily basis. And they weren't like all data cleaning functions. They weren't all data viz functions. So RUF, Random Useful Functions, emerged. And like that, you can host packages in other repositories. So like Amazon now has like a package repository. I think GitHub does as well. So in the future, there will be more places, more app stores, if you will, where you can put R packages. I think the 2 that you should know today are CRAN, which is the official source, and then getting things through GitHub using the package called DevTools. Now, related to R is this idea of RMarkdown. So we talked about Markdown syntax early on, and that's like the superset language. RMarkdown is a flavor of Markdown, specifically with some built-in features to work specifically with R. Just to pause for a second, quick show of hands. Have you ever worked with Jupyter notebooks before? Okay, so our Markdown files, if you have worked with them, are exactly like that. It's a cell-based way of running code. For those of you who haven't used our Markdown, we're actually going to go into it in just a bit. But it's essentially a way that you can specify chunks of code rather than having a long piece of code that you just hit run and it all runs together. You're actually running specific sections and you can run them one at a time. You can run them out of order. And so it's a way of organizing the code that lends itself better to communication. So you can interject narrative, like you can write like paragraphs and then interject a plot, or you can write your narrative and interject a formula. And so if you've ever worked with LaTeX, I think it is, it's very similar. You're integrating narrative, code, plots, all in one document, rather than generating something in R, hitting copy, going to Word, pasting, and doing that manual process. You're doing it all at the moment of hitting knit or save or compile. So what we're going to go over next is the RStudio interface, because I think it's important to kind of ground everyone in some of these simple things first. This is the scripts panel. So on the scripts panel is essentially where you write one-off R scripts or R Markdown scripts. The top right, you can have your files panel. So this is like if you opened up your Windows File Explorer or on Mac, the Finder, it would be the same files that you would see there, although it's just all in one place, so you don't have to have multiple windows to see things. You have the console where you can run one-off commands. So if you're like debugging something or just wanted to like inspect an object to like understand what's happening inside of it, you would maybe do that in the console. Then on the right, you have a plotting window that would show any plot that you generate, whether it's in the console or in your scripts. Oh, I know I did that. So just a quick aside, if I'm talking about the plot menu, there's this really great book called The Truthful Art that goes into all the ways that you can use data visualization to effectively communicate, and unfortunately, all the ways that you can use data viz to make something seem one way when it's actually something else. And so this is just my short PSA on the 5 qualities of great visualizations. The first is that the data visualization is truthful. There should be transparency in the decision-making and the reporting of the data. And so if there's a lot of missing data, you should show that rather than obscuring that, as an example. Great visualization should also be functional, so they should be understandable and uncluttered. So it should have just what the user needs to see to understand the information and not extra things. Plots should be beautiful. I very much resonate with this one. I have a close colleague that I work with that has an organization called Playing the Archive. And if this works, so Playing the Archive is very much hinged on that idea that data visualization could be art. And so my colleague Neelam Ram and some others, Robin and Joey, have developed over the last few years visualizations from child development data and watching mothers and children interact, data from studies about emotion dynamics, and all of this they render as sound. So they'll have musicians play the plots, like things like that. They'll have art sculptures that are created from data from different people. And so very much resonates with this idea that data can be art. So these are, if I'm not mistaken, children, sorry, the one right before was like children and mothers playing in some kind of like toy-based activity. Here are longitudinal data as wood sculptures. So you can see change over time, like going forward or backwards in the wood sculpture. So anyway, that was just more of a short plug to a colleague that very much resonates with this idea that data is art. Data visualization should also be insightful. So they should be revealing some kind of trends or relationships. And lastly, if you've done all this right, then the visualization you've created is enlightening. It carries forward information that the person can ingest and communicate to others. Now, that was just, again, a short plug for data as art. So if any of you all like want to talk more about that, I'd love to. It's something that I've been playing with for a few years. Now, R also has this help tab where you can actually get help for specific functions or an entire package. It's the source to get helpful information, and I'll show you other ways to pull this up. Then there's the viewer. So it looks similar to a plot that it's rendering visual information. When you're rendering tables in R that are like HTML ready, they'll render in the viewer. And the viewer has this button here that actually pops it out and opens it in your default browser. So it renders that as HTML code. You can copy that HTML code and paste it into a Word document, and it would look almost exactly like that. Or you can copy that HTML code and put it on a website. And so it's very flexible, especially helpful if you're writing manuscripts that have a lot of tables. Now, what I'm going to get into now are some really simple shortcuts before we get into the actual code in a few minutes. The first shortcut that I just absolutely love is this idea of being able to press Command Enter or Control Enter on Windows to run a piece of code. So I almost like have like a game in my head where I try to use the mouse as little as possible. So I've learned all the keyboard shortcuts of things. And this is one of my favorites. So I can basically highlight a piece of text or all the code and press Command Enter, and it runs, and then I have all the results. Or I can highlight one line, Command Enter, and hit run. It saves me from having to do the visual search activity of trying to find the run button wherever it is and then hitting run. Another shortcut that I think is just phenomenal for code organization is this idea of adding 5 hyphens inside of a comment to create a shortcut. So just as an example, I have a comment in here somewhere that says install packages from CRAN. And you'll notice that then I can step through the rest of the chunks of the code, and I can, so to speak, fast forward to the generate a sequence piece, or go backwards and see what was happening in setup. Without this use of hyphens, you're literally left just crawling through your code manually without any organization. So I encourage you all, as you're writing larger code bases, to use this to help you navigate your own code, but as also to help others that are navigating your code. Now, a lot of what you saw is mostly based on how I use RStudio. That layout is not the default. I've kind of reconfigured it in a way that works for me. And so if it doesn't work for you, I'll show you briefly where to change that. So in the tools, in the global options, you have the ability to go to the pane layout and essentially reorganize those panes however you'd like. My mental model with R has always been that the code's on the left. If I want to double check something, it's right below the code in the console. And if I want to see my results, it's on the right, kind of going like from left to right with respect to the generation and then the output. So again, that's just the mental model that's worked for me. You might find that a different layout works for you. So I encourage you to check out the options and just kind of play around with that. Similarly, in the appearance menu, you'll notice all the different color schemes that you can use for your code. I do a lot of my programming at night, so bright screens are frustrating and annoying. So I tend to use dark mode, specifically the Darkula theme. It just very visually appealing. So anyway, that's just kind of my short plug on customizing RStudio and making it something that you find enjoyable to work with. All right, so in just a second, we're going to jump into R, but before we do, I want to just kind of start with some very simple data structure primitives. So if you've not worked with programming before, some of these concepts might be a little bit foreign, so I'll just kind of step through them slowly. You have character data, which is basically the same as saying text data. So words, open-ended responses, that would all be character data. You might have an issue sometimes where you read in some data from like an Excel sheet, and it's a number, like it's 2.47, but it's in quotes. That is now a character number, and you need to convert it to a numeric to actually do math on it. And so we'll go into type conversions today, but at a high level, character data is quite literally any string, any set of alphanumeric and symbolic characters. Numerics are all real numbers with and without decimal places. So that's any number. You have integers that are real numbers without decimal points. And so whole numbers 1 through 10 as an example. You have logicals, which are things like true and false. And so it's a set of states, and it's either one or the other. You have raw data, which are the raw bytes of data that underlie the data that you're working with. So if you're working with image data, it's the raw pixel values for each RGB channel. A list is a named or numbered array of entries. And so it's a collection of maybe similar things, although lists can actually be of mixed type. Then we have a data frame or a tibble, which are these rectangular representations of data, or what I previously called tidy data. And then we have vectors and matrices, and those are more so special topics that we'll get into now when we look at the code. Now, this is more of a thought exercise, and I'd rather get to the code. So I'll just kind of pause here and we'll spend a couple minutes together thinking about this pseudocoding exercise. So those folks that are with us on Zoom, feel free to kind of participate in that way by just typing out how you think you'd approach this. Part of why I'm starting with a pseudocode exercise is because I feel like programming can be intimidating, especially when you don't know the words you should be using to accomplish your action. And so I want to kind of ground you all by saying, you don't even have to think about the code. Just think about it in concept space and a linear set of operations. How would you accomplish your action? And often when you start with pseudocode and kind of specify out those discrete units of transformations and calculations, then translating it into R or into Python or who knows, C++ is actually pretty easy because there are specific actions that you're doing, and almost every programming language has a way to render an image from pixels or vice versa. And so what we're going to start with today is a pseudocoding exercise where imagine if you allowed participants on Qualtrics to enter state of residence as free text entry, resulting in Alabama, spelled as AL, capital A, lowercase l, Alabama with the capital A, Alabama with everything in capitals. And then ideally, for the type of visualization you want to do, you ideally want them to all be 2 uppercase letters. So just for maybe a couple minutes, think about it. And then whoever wants to describe their pseudocode approach, feel free to either unmute yourself, or if you're here with us, feel free to speak up. John?
Assuming one of them entered something spelled incorrectly.
Yeah.
Big something. Take the first 2 letters of every entry and make those all caps and make that the new. Make that like column of data.
You got it. That's essentially it. And so for those on Zoom, if you didn't hear, essentially take the first 2 letters, regardless of whether it was a 2-letter state abbreviation or the whole state name. That solves the problem, and you now have the first 2 letters, and then you write some code to make it uppercase, and now you have 2 capital letters for every entry. Thank you, Sean. So I think as you approach any programming problem, think of it in this way. Just break it down into words. If you were going to have to explain it to a friend, a colleague, how would you explain it? And how would you problem solve it agnostic of software? Pretend R doesn't exist, pretend Python doesn't exist. How would you conceptually, almost on paper even, solve this problem? And once you've done that, translating to any code base, like I said before, is as simple as Googling it, or realizing that, oh, you need to make it uppercase. That's a string transformation feature. How does string transformation work in R and Python? And then that's a simple Google search, and your answer is apparent at that stage. So anyway, I think programming could be intimidating, but especially if you don't pseudocode. So I encourage you all, as you're working through your programming problems, to think about a way to build in pseudocoding. All right, the moment we've all been waiting for. We're about to go through some R code. So bear with me here as I get set up. The code is in the GitHub repository that I shared before, and it's going to be specifically Markdown files 3, 4, and 5. 3 is R basics, 4 is R pipeline, and 5 is date manipulation. So just before we get started, confirming folks on Zoom can see the screen. Thank you. All right, so just by way of orientation, this is an RMarkdown file. One way you know that is the suffix on the end of the file in the top tab. Another way you would know that is by looking at the icon, which is unfortunately extremely tiny here on screen, but it has a red circle, and inside of the red circle it says RMD. Just for a second, I'm going to create an R script So you can notice the icon difference. So an R script is a blue circle with the letter R inside, and RMarkdown is a red circle with the letters RMD inside. If you have the blue circle, what you have is essentially a one-off script that runs top to bottom. If you have a markdown file, you have something that could be generated as HTML, as a Word document, as a PDF, as a PowerPoint presentation. And so it's more flexible in its output, whereas R scripts just echo the output in whatever way you prescribed. So I thought I'd start there. All right, so as an overview, this is me describing how to do very specific minor things in R. And I don't mean minor in that they're not important. I mean minor in that this isn't like a pipeline. We're not working through a data analysis problem. I'm just creating contrived examples to show you how to do specific things in syntax. On Friday, we're actually going to go through a pipeline where we apply these techniques. So the first thing that I want to show you is one way to install packages. One way to install it is by using the install packages syntax. And so you would then specify a vector of packages. And so here, when I say that something has a C in the front of it, and then I open parentheses and close it, everything inside of that is a contents of a vector. So let me actually, before we get into that installation of packages piece, let me just kind of create a vector example. So in this case, I created a vector with the entries 1, 2, and 3. You'll realize that I put the 1 in quotes, but I didn't put the 2 and 3 in quotes. Something happened. The vector realized that there's an initial type, so in this case, a character, and so it coerced everything else to also be character. So it made the 2 and 3 character. Now I can also specify a vector and have it fully be with numerics as an example. And so now, given that all of the values are of the same type, R determined it to be numeric, as shown here on the right. And so you can create vectors of numbers, vectors of strings. And so that's how we're using the install packages feature. We're creating a vector of strings where each string is a package name. And then we're installing all the packages in that vector. In this case, I'm not going to run it because it might mess up my R environment for the workshop for today. So if you wanted to run it, you would just grab the code from this code block and paste it into the console. Now that's how you would install a package in code. You can actually also install a package using the packages menu on the right. So you have easy buttons like install and update. Let me think of one. So there's this package called mass. I can install it by something as simple as what I did here. It's important to point out this point about dependencies. So some packages depend on other packages. And in that situation, you always want to have this install dependencies checked, because if not, you end up with a package that doesn't have everything it needs to run, and then it just won't work. So it's important that you keep install dependencies checked. There might be edge casey situations where you want to keep ggplot version, I don't know, 1.02, but then have this package that depends on ggplot 1.15. And so there might be specific situations where you might say, no, I don't want to install the dependencies because it might mess up an operation inside of another package. So this is the part of R that I'll gloss over for now because it sounds maybe messy, and it is. But I'll get into how you manage your packages a little bit later in the workshop. For now, just showing you how to install them. Now, I put together a list of some of my favorite R packages. So if you wanted to install them in one go, you would just copy this vector or this piece of code with the vector inside. And then that would install tidyverse, which is a universe of packages that we're going to use a lot, and I'll go into shortly. DevTools, that's used to install R packages from other sources like GitHub. Qualtrics, to specifically work with Qualtrics data. TidyText, text data and topic models to work with all open-ended data. Same with WordCloud and GG WordCloud. LME4 is used for multi-level modeling. SJPlot is used for rendering tables from those multi-level models and regression models. Janitor is a package to do data cleaning. So when you have really messy column names, Janitor is going to be one of your best friends. You have squice, if I said that right, which is a data visualization GUI. So someone actually built out a GUI on top of the RStudio GUI that allows you to like drag your data into like the x-axis or the y-axis, and it just generates the plots for you. So as you're learning how to do data visualization, it's a helpful tool because it gives you what you want. You got the plot that you're looking for, the appropriate color scheme, but also generates a code snippet so you actually can learn how to do the same thing in code in the future. Then there are packages like Rio, which are to read in multiple files at once or export multiple files at once. Calplot to stitch together multiple visualizations. Stringy to work with character or string data. And finally, digest for snapshots of data by taking what's called the hash of your data. So these are all things that we're going to use throughout the workshop, and some of them in just a couple minutes. So just curious, how many of you have heard of this idea of a random seed in any of your experiment development activities before? Okay, so let me spend some time talking about random seeds. If you want to randomize people to two conditions and you don't have a random seed, then what you've done is not reproducible. You will get a different result every single time you run that code. Every time you run it, it's a different randomization order. The second you set a seed for your randomization, it becomes deterministic. So now I set the seed to 1013 and I randomly generate 100 numbers. Whether you generate them or I generate them, it's the same 100 numbers. So when you're doing things like machine learning and you're dividing your data into training and test, and you're randomly sampling to generate a test set or a training set, and you want someone else to reproduce the results, like your advisor, you want to make sure you set a seed so that that reproducibility is possible. What I'm doing here today is generating a bunch of like fake text files. And without this piece of code, every time I committed to GitHub, I was getting a new set of text files because the contents were always changing. So now that I've set the seed, it's the same files every time, and I don't have to like write a new git ignore every time. So anyway, I'll go ahead and run this piece of code. And all it does is behind the scenes say, hey, randomization engine, whenever you need a value for a seed, use this one, in this case, 1013. It could literally be whatever you want. I defaulted to my daughter's birthday. You can pick quite literally whatever you want and it'll work. Now, let me kind of go over a couple other high-level points related to our syntax. And the first is getting help. So I showed you before that there's that interface where I can just go here and hit help, and I can search and I can find whatever I need help with. You can also do that in code in two different ways. You can wrap a function name or a package name in quotes, and then wrap that in the help function, and it'll open up the help tab to that section. You can also do the same thing, but not put it in quotes and reference the exact function name. So when I say question mark dplyr : mutate, I'm asking for help on that specific function from that specific package called dplyr. The same way that if I wanted to get help on the whole dplyr package, I would just say question mark dplyr. So there are just different ways of getting to the same place. I just, for whatever reason, have encoded question mark into my thinking. So that's how I get to the help menu, but any three of these ways will work. So if I were to run this help, I would get the informational page about the digest package that shows the description, how I would use it, what are all the arguments that I would need to use if I want to use this package, all the way through how they like manage changes within the package. So if you want to write up a manuscript and you use a certain package to do a highly specific thing, you might also find the citation for that package inside of this help. There's another way to get to the citation. You can actually type the word citation and then pass in the package name. So in this case, I'll just say, give me the citation for digest. And there it is. So now I have a full, in this case, markdown ready citation for this package that I used. And so this allows you to capture and acknowledge and credit folks that have created the packages that you're using for your analyses. So when I'm writing a paper and I use 10 R packages, those now become 10 references in my reference sheet. So again, I'm showing you how to get help in R, also showing you how to get citations in R. Before we jump into much more that's highly specific, I'm going to go over 2 other concepts that are helpful to know early on. One of them is this idea of case sensitivity. So a lowercase a and a capital A are 2 different variables in R. And that's really important to know early on because you might end up with a situation where you created data with a capital D and then data with the lowercase d, and you think they're the same, but in essence, they're actually 2 different copies of the data set. So again, just exposing that R is in fact case sensitive, so capitalization matters. So in this case, my contrived example is apples does not equal bananas. And I can say that differently by saying, does A equal A? Does lowercase equal A? And in this case, it's false. Apples does not equals bananas. Related, one of these just kind of high level concepts to understand about the syntax is this idea of variable assignment. So if you're curious and have some time, there's actually a whole article about why R came to this decision. But in essence, I'll sum it up by saying the intended way to assign a variable in R is to use the arrow operator. So open caret hyphen is an arrow, like I show here. But then eventually they noticed that enough people were getting hung up in R by typing equals, because that's what you would use for variable assignment in almost every other programming language. So it was like somewhere around 2003 or so, they released this equals as an assignment operator feature of R. So now actually you can use the arrow assigner or the equals assigner. They kind of do the same thing. How I use it in practice is that I use equals whenever I'm setting constants. So if I'm saying like the threshold for outliers is 2 standard deviations, I'll make threshold for outliers all capital. I'll say equals by using the equal operator, and then I'll set it to whatever the value is. If I'm creating a variable, I'll use the arrow operator. So that's just my preference. Fundamentally, internally, they're doing the same thing.
So that's when you go back and look at your old code, you're like, oh, this is a constant, and this is not. It's not in the console, it makes no difference, right?
Exactly. It makes no difference in function, but conceptually, organization-wise, I find that to be helpful. Like these are all the things that drive action in my later part of my script. So I want them to look a certain way. So that's why I always capitalize them and use equals. It's like redundancy in the fact that they're different from the other variables. So if that wasn't confusing, I'll show you that basically you can set x equals to 3 in all 5 of these ways. So all of these work. This is probably the preferred syntax, line 65. It's called leftwards assignment, but apparently you can also do rightwards assignment if you want to give people a headache when they're looking at your code. This last one though is a little bit different, so I want to pause here because it exposes something really important about R. Up here in the top right, you have an environment. Each package has its own environment. There's a global environment, and you can create additional environments. If you want to, for example, have an application that has what I would call internal data that only like the application state and how it's running, but you don't want to expose any of that private information to the user. So you would have some variables being assigned to the global environment for like everything to be seen. And you might have some variables written to like a secret environment for just the actions of that web application. That's a little edge casey, so I'll gloss over that for now and say, if you use what's on line 65, that'll work for all your code, as well as line 67. The other ways of doing it are just more like ways that work, but most people don't do them in those ways. So in this case, I'll assign B equals bot and C equals bot, and you'll realize that the result is the same. They're both a character string with the word bot inside. And in this case, I assigned x to 3, the value of 3 in 5 different ways. And if you look in the environment, x equals 3 every time I run this code. So I can assign things in R in many different ways. Pick your preference and just stick to it. My preference is line 65 for any variable, except the constant. And in that case, I would use the version on line 67. All right, so now we're going to start applying some of these concepts to create a bunch of, so to speak, contrived example data structures. So I'm going to create a double. I'm going to create it as an integer first, and then I'll create it as a decimal point number second. I'll then create a logical by assigning it to the value of true. I'll create a date by wrapping it in this function called asDate. I'm wrapping a string. Then there's a list, which is either a named or a numbered set of entries. So in this case, I chose a named set of entries like x equals our norm, which is generating 100 random numbers, y equals our norm, which is generating 10 random numbers. And I specifically set it up this way with a different length value for x and y to show that lists are okay with that. They're immune to that difference in length. Now, if you're creating a data frame, it'll also work, but then you'll have a bunch of missing data. And so you can create structures with missingness as simple as like I did here. And then I think we went over this just a bit ago, but creating a vector is done by essentially putting the letter C around the set of parentheses and then inserting values of a common type. If you don't insert values of a common type, they get coerced to the first type in the vector. So I'll just run this code now. And so everything that I'm doing is being echoed over here in the environment, but it's also being echoed here in the console. So I'm pressing Command Enter to run each line at a time. And so you'll start to see the items that I'm running emerging on the right side in the environment. So what I just created were a couple data frame objects, and then we had a bunch of value objects. So I just want to pause to point out that the environment is broken up into these headings where you have data, like as we'd refer to tidy data. And then you can actually click any of those and look at it. So it almost becomes like Excel in that way. And then you have values that are just unitary values like a single variable or a list or something else. So if you're looking for something and you can't find it, make sure you're in the right heading. Like if you're looking for a data frame, it should be in the data heading. Or if you're looking for just a character value, that should be in the values heading. And so that could be confusing at first. Now, one of the things that you're going to run into a lot with R is you think something is a certain type, like you think it's numeric, and actually it's a character string. And that's problematic because you need stuff to be in numeric if you want to take a mean or you want to take a standard deviation. And so it's really important to know the types of your data before you start to work with it. So R has this function called class that you can apply to any variable. And it'll start to describe to you the formats of those data. So as we recall, the number 1 is a numeric, and so that's what it echoed out to me as its class. The same thing with 1.0, that's also a numeric value. Then there are logicals. Logicals return the logical value type. Dates return the date type. Lists return the list type. You get where I'm going with this. It's just, I'm showing you how to create each variable type, and then I'm showing you how to verify that it got assigned to the right type. So this should show me that it's a data frame. Tibbles are a funny situation. What did I do? There we go. Tibbles are funny in that they're actually 3 types. And this is something behind the scenes that's done in the package creation to make these tables interoperable. So TBL is a tibble, and that's what the package developer decided to call his version of tables. And there's a TibbleDF, which is some hybrid format. And then there's data frame, which is the base R way of representing rectangular data. So tibbles are weird, but they in essence operate like a data frame. And then in this case, the vector is numeric because the values inside of the vector are numeric. Okay, so again, this is just explanation of data types, and that'll become more important the more we keep going in the workshop. So next, what I'll show you how to do is generate sequences. So if you're working on experiments that have, you know, 1 distractor for every 100 targets, you might be able to find a way to generate a sequence to render that stimuli set. You can also use it to generate sequences of numbers with certain spacing. So just as an example, I can create a sequence from 1 to 100 by using the sequence function and specifying the by operator to be by 1. And so if I were just to inspect that object, you'll see that its values from 1 to 100. You can do the same thing, 0 to 1 by 0.1s or by 0.001, whatever you need it to be, it's flexible. I typically use this if I'm generating what I would call a linking table, where I have my experimental data that has the actual data that I collected, so participants 9,000 through 10,000, let's say, or that was at least the expected range. But then let's say 500 people didn't show up to the experiment. I have 500 records of missingness. And so if I generated a sequence from 9,000 to 10,000 and merged it with my data, it would expose to me where the missingness is. And so I often use sequences in this way to find where people were non-compliant or non-adherent. I've also used it to generate stimuli for an experiment. Like I want people to see, numbers from 0 to 100 in groups of 5 or spacing by 5. Let me show you another way that you can use sampling to generate stimuli. So if I, for example, had a list of things to sample, like this list here, the letter A, the number 1, the number 2, and the letter B, I can use the sample function inside of R against that list and say I want the result to be of size 1 to get 1 value back. In this case, it randomly sampled and the value I got back was A. If I run this again, I should get another value, et cetera, et cetera. So that's how I would sample values without replacement, but I can also sample values with replacement by passing in the replace operator being true. And so you'll notice something on line 105 and 107. It's the same package call or the same function call, except one has an additional parameter. To get familiar with the different parameters for the functions, that's where I'd encourage you to use the equals operator, or sorry, question mark operator, to inspect the functions inside of base R. So all the way at the bottom. So this is a base R package from, and here's the function called sample. Here's all the syntax that you need to know about its usage. Here are all the arguments you can pass in. So I'm only passing in the bare minimum for this to run. I could do more. And a lot of packages and functions work in this way where they expose to you just a bare minimum to get started. And you might find that there's almost like cheat codes built in. So I encourage you, for any function that you're thinking of using, to read the documentation and make sure that you're, number 1, using it appropriately, and number 2, not recreating the wheel when there's just a parameter for something in the package. That's something that I've done a lot of, unfortunately. Yeah, Stephen?
When typing in functions, do you actually have to put, like, for example, sample value? You could list the sample as the variable, and then you put comma size equals 1. Can you just put 1 and it's in the same place? It knows to grab 1 instead of typing that all out.
You could. Where that becomes problematic is more in the aspect of readability. So now I almost take an assumption implicitly, like it's here, so it should be size. But let's say they rewrote the package and they reordered the parameter names. Now size is no longer size. Now it might be I don't know, probability. So now your logic got inverted by a package change. So I always err on the side of being hyper specific. So name equals thing value.
So let's say you wanted to use not size, but just replace. So you could just put comma replace equals true and omit size and do something that doesn't need size there. Or something like that. You see what I'm saying? Like you want to skip an option.
Gotcha. Okay. Yeah. I mean, I think size might not have a default. Yeah. So size doesn't have a default, so it actually shouldn't run. Or maybe it defaulted to 1. Sample. Yeah, so I guess the default of size is 1. So yeah, that's where this gets tricky. You need to know what those defaults are before you start doing things like that. If you blindly don't pass in options, you may not get the result you think you're getting or you intended to get. So I always err on the side of just being hyper specific, specifying all the parameters for each function where possible.
Gotcha. If you don't care about that option, you could, is there a nan or a squiggly, I don't know how to do in this language, but it defaults to 1, but you can admit it does 1. Is there something else you can say? I don't care. Put the default, size equals that.
So in this case, if you're okay with the default being false, you don't have to pass in this option. And so in the usage, they'll normally specify what the defaults are. So here it's saying replaces false is the default, the same way that null is the default for probability. So like I don't have to specify probability. I do need to specify replace if I want my value to be anything other than false. So yeah, so it's really important that like any function you're using to read the documentation carefully to make sure you're not misusing it.
Yeah.
Because sometimes like the name of a function leads you to think it does something, but it's actually different or counterintuitive to how the developer thought about it. So yeah, I'll continue. So next up, we have file operations. So one of the things that I have to do a lot in almost every single project I've ever worked on is read a list of files in a directory. So all the CSV files for this experiment or all the eye tracking files for another experiment, they typically have a common suffix or file extension. And so with a set of code like this, I can list out the files in a certain directory. So let's do that. I had to do a hacky thing there real quick where I said /data because the data folder is in a different location from where I wrote the textbook. So I'll fix that and make sure everybody gets it. But in essence, if you call list files, specify a location, specify a pattern, you'll then get everything in that directory. If you specify recursive equals true, it'll go inside of every subfolder. So if you have data that's nested 10 folders deep and you list recursive equals true, it'll find every one of those files as deep as it goes in the folder nesting. If you specify recursive equals false, you're only going to get the stuff in the topmost folder. And so that's really important. And I often try to avoid nesting my folders where possible. Like the most nesting I'll do is maybe a data folder with like subfolders by type inside, but maybe no more than that. But if you do have folders that are more nested than that, you'd have to use recursive equals true to find all of those interior files in all of the subfolders. Okay, so that's how you would at least find all the files that are, in this case, all of the CSVs. I can do the same thing and just say, give me all the files, like we talked about earlier by saying star. Just give me all the stuff. So in this case, it read out more files now because I asked it for more than just the CSVs. The same way that I can look for files inside of a folder, I can actually also find if certain directories exist in my project. So like this project should have a data directory. And this will actually probably say false first, and I'll explain why. Because in this project, right now, we are inside of the Context Lab Reproducible Science Workshop scripts folder, and it shows here in the console. And because I'm inside of the scripts folder, data is not in here. Data is actually one folder up. So to go one folder up in code, the syntax for that would be ... /. And so now I'm saying, look for data one folder up from the folder that I'm inside of. And so now the data folder exists. So I'm going to actually leave it this way because I think it's helpful. And then the same way that I can check if a directory exists, I can actually create a directory. So I can create a directory now called test. In this case, I'll just put a file inside of it just for this exercise. And so let's go and find that test directory. So given that I didn't go up a folder, I actually created that test directory inside of my scripts directory. With this last bit of code here called unlink, I'm actually going to remove the folder. And so it's that simple to not only look for files of a certain type, create folders, but also delete folders. It's only quite literally one line of code. So if you, for example, needed to programmatically generate 1,000 folders, you can create a for loop with this syntax inside and create those 1,000 folders without having to actually go in Windows File Explorer and create file by file, folder by folder. So that's a very generic file exploration. What we're going to go over next is reading in and writing files. So R has 3 packages that I think are going to be immediately helpful if you work with Excel data, tabular data, or SAS or SPSS data. And those are Read Excel, Read R, and Haven. Haven is a package to deal with all the foreign formats or all the formats that are not interoperable. So Haven is what houses the SPSS function call, the SAS function call, and there's probably actually others in there. So these are the packages that we need. And now for this exercise, what I'll do is create just a simple data set that has an X and Y column and then a study ID column. The X column has 100 random numbers, the Y column has 100 random numbers, and then the study value is the same for all rows. And so I'm in this call right here, generating a data set in code. So if I run this, I should be able to come back up here to my data part of my environment and see the code where I have 100 random numbers in X, 100 random numbers in Y, and the study value repeating from row 1 through row 100. I did that because I wanted to show you how to write files or save files to your environment. So I created a fake data set. And in this next stage, we're going to write it out into various formats. So I'll write it out as a CSV, as a delimited, tab delimited file, as an SPSS file, as a SAS file. So now I created my exports, and I can give them to any collaborator. They have it in whatever their preferred format is, whether it's SAS, SPSS, or CSV, it's all there. So in 5 lines of code, you can export your data into whatever format you'd like. If I had 6 lines, I would have shown you how to generate JSON data, but that's a topic for another day. So I'm basically generating fake data, writing it out, and in just a second, we're actually going to read it back in so we can go through the full circle of data processing or file input processing. Before I do that, I want to show you something that I only recently learned about. It's this package called Rio. It's intended for like input output in a sophisticated way to do everything with a little amount of code. To say that differently, I can actually generate an Excel workbook that has sheets for every item in a list. So in this case, what I decided to do is to make 3 random data sets. I just generated 10 random numbers in each. I assigned a data set value, 1, 2, or 3. And then using the Rio package, I'm exporting to this file that I named, in this case, 1 Excel workbook with 3 sheets. And then the X value is the list that I want to save, where every item in the list becomes a sheet in Excel. So in this case, the sheet is going to be called DF1, there'll be another one called DF2, and there'll be another one called DF3. And the contents will come from each of these data sets that we created on lines 170 to 172. So let's go through the motions and let's look at that data set. And again, that would be in the output folder. So this is where I need to, I think, actually open it up in Finder. So again, it created 3 sheets of an Excel file, DF1, DF2, DF3. The way that I would use this in production, so to speak, would be generating a sheet for all the trial level data. So if I got all my participants and stack them and put that in a data set, I might put it in a trial level data set. I might have a second sheet, which is participant summaries, so a mean for each person. And imagine I have a third sheet that is the data quality report. How many variables and values are missing in this data set? And so I can hand over one Excel sheet that has everything a person will want to look at if they're working with this data. This violates the interoperable piece because I now created an Excel file that works in Excel, but it's a principle that I'm okay with because it helps the end user see everything in one place. So anyway, this is the Rio package. Let's see. So The Rio package has the ability to write out files into almost every format imaginable. And in support of that, they have a function call called install formats. So in case you want to do something beyond Excel, beyond CSVs, beyond text files, you'll have to install the install formats package to do that. So that'll be if you're working with like big data and like a Hadoop file storage system, or working with more of MATLAB data, or even geospatial data that's binned into like hexagons. Those might be situations where you need to install special packages to deal with that data. Otherwise, Rio out of the box does what I showed you here today. Maybe I'll pause here. Is there anything that I can clarify? Anything that maybe I can go over again? Any questions maybe? Yeah, Stephen?
Something I can't figure out is how do I view my current path? Because I see the output, but like I didn't have a file named output. So like, or folder named output, so I can actually put it in there. So I'm trying to figure out where the heck I am right now.
Gotcha. So there's a function call called getWD, get working directory. And so if you type that, it'll tell you exactly where you are. So in this case, the output is the same as this line in RStudio. So both places will show it. I find that the font here is really tiny, and especially if you have really long folder structures like I end up having sometimes, you're better off typing out getWD to see your path.
How do you set a path like a default path? Like let's say on all my stuff in R, where is it? RStudio like preferences or something like that? Or
Yeah, so that's inside of the global options. I'll say a couple other things though, because that's a really good point. So R has the ability to generate projects, and I think we'll get to that in a few minutes, hopefully. But basically, when you generate a project, all the paths become relative to that folder structure. So imagine you create a project, and you have a data folder and a scripts folder. You don't have to type out like C, users, Nelson, whatever, data scripts. You just got to type the word data or the word scripts. So if you don't use our projects, Stephen, like you were mentioning, you're stuck dealing with path yourself. And that's where our code gets really annoying to deal with in the long term. So I've erred on the side of doing everything inside of an R project so that all my paths are relative.
okay.
And I'm not like setting and resetting the path over and over. If you look at a lot of my scripts from like 5 years ago, that's how I did everything. Like, all right, we're here now. All right, we're going up now. We're going down a folder now.
Yeah.
And rather than that, I'd rather err on the side of projects that have relative paths. And so hold that thought. We'll get back to that in a minute. Let me just check Zoom just to make sure there's everything seems okay on Zoom. All right, so another package that I'll go over now is the janitor package. It's a data cleaning package, so I just love how they named that. This package allows you to do a lot of cool things. The part that I use the most is the column name cleaning function. So imagine a situation where you have a data set like janitor before, where you have a really, really long column name with spaces and mixed case. That's going to be a lot to type out every time we need to reference it. So that's an issue in and of itself. Then there's column name, which is all capitals with underscores. And then you have group $$, which has special characters now. So I did that to show you that with one line of code, in this case, janitor clean names. Oops. You then end up with everything in snake case, which is lowercase letters, underscores, no spaces ever. And so the really long column name got cleaned up. The column name with special characters had the special characters stripped out. I'm now ready to do things with this data and not have to worry about making sure to remember to put a space in my file name every single time I type it out to do an analysis or to do a pre-processing step. So when I'm working with new data, one of the first things I do is run it through this janitor function. Now, in the previous steps, we generated a bunch of random data. And in the next set of lines, we're actually just going to read it all back in. So using the readr package, there's a function called readCSV to read CSV files. It has a parameter called NA to specify what the NA value is. So in your Excel file, for example, or your CSV file, you might have a period. And so period then becomes your NA value. For some folks, NA is when the value itself is missing. There's nothing inside of that cell. And so this is where you just need to be mindful of what system generated this data and what does a missing value mean to you and to your data. Is it a period? Is it a comma? Is it the word missing? And so just highlighting that you can read in your data in many different ways. Again, as CSV, as a tab delimited file, as an Excel file, as an SPSS file, and ultimately as a SAS file as well. I ran into some weird issues with the SAS syntax, so I wasn't sure there's going to be a lot of SAS users, so I kind of gave up on it, but I want to fix it because I know you use SAS and others use SAS. So that's kind of, so to speak, a bug in the code right now. So what we're going to go over next are very common data operations when you have many different data sets. It's awesome if your project only has one because that's really simple to deal with, but as you kind of head out into production, into different research settings, you're going to end up with probably dozens of files spread across different systems. So like as an example, I do work with folks that have mild cognitive impairment. I often have neuropsychological diagnoses, and that's in one file, demographics in another file, trial level cognitive data in another file. And so these are all data of various types, various lengths and widths. And then there's a step somewhere where I actually need to integrate it all. I need to merge it all. It all needs to be in one spreadsheet so that I can do my analyses. And so part of what I'm going to show you here is with very simple data sets, how to do that. So the first thing that I'm going to do is create 3 data sets and stack them. This is analogous to the idea where you have a folder of participant data and you need to stack every file together. So you have one file with all your trial level data. So we'll go ahead and create those 3 data sets. There's this bind rows function inside of R coming from the dplyr package that allows you to pass in a list of data frames to merge. And so in this case, I'm going to create a df all variable and bind the rows from df 1, 2, and 3. And so if we're following the logic, we should end up with 30 rows and 2 columns. And so let's go ahead and look at df all. And we end up with 30 rows and 2 variables. So as intended, we now stack these data sets together. If I had 1,000 participant files, I would probably do it a little bit different because I'm not going to write, bind rows df1, df2, df3. I might do it in some kind of for loop. So if that's helpful to anyone, I can go over that maybe on Friday. But for now, I'm just kind of going to stick with these simple examples. So that's stacking data. That's a very common data cleaning operation. You have a bunch of files. You need to quite literally vertically stack them as if you had pieces of paper and you're stacking them on top of each other. Now, there's also the idea where you need to join data sets by a common identifier. So you have, let's say, driving data on some folks, and then you have their demographics. They live in 2 files, but each file has an ID column. So you can merge onto that ID column. So for example, I'm going to make a data set that I would call my linking data set. Imagine this is demographics. So it's simple. It just has a data set ID and a description. Imagine that's a participant ID. Now I can merge that linking table on all the data that we had created up above by inner joining it. And if I did it that way, I only end up with those 30 observations. If you look at the linking table, you might have noticed that I have an extra data set 4, Mach 4. Since the data itself only has Mach 1, Mach 2, Mach 3, the one that I didn't have got dropped. And so an inner join drops what's missing on the right. That's helpful sometimes because you don't want any of that extra data if they don't have the main data set you care about. But sometimes you do. Sometimes you want to know how much missingness you have. And so what you would do instead is called a full join. We're going to go over joins more on Friday, but I thought I would just kind of preview the idea now. So a full join in this case will give us 31 observations. We have data for 10 rows for each of Mach 1, Mach 2, Mach 3. And since we don't have data for Mach 4, all we have is the linking table value for Mach 4. So imagine this was participant data. This would be a situation where the participant didn't do your cognitive experiment, but they did have demographics. And so it depends what you're trying to do, which join makes the most sense. 90% of the time, inner join is what you want. If you're worried about missing this, you'll probably be using a full join. That's not the full story. There's like 8 joins that you can do. And that's part of what we'll get into more on Friday. For now, I just wanted to show you that this is how you would link data with a common identifier. All right, another common data operation is binning data. So if you have values from, let's say, 200 to 1,000, and you want to group values 200 to 500 into group 1, 500 to 1,000 into group 2, you would use a binning operator. And so I'll walk you through how that works mechanically. So you end up with, let me just get this created. So I'm going to create a data set to bin, and it's just numeric values between, in this case, 500 and maybe like 700. And I want to bin them into some categories. So I can bin them into categories by using the cut operator in R. So I'm basically saying cut X, which is that variable randomly generated, with these breakpoints, so that way I end up with a group from 0 to 300, 300 to 400, 400 to 500, and then et cetera, 600 to infinity. So I'm creating like a tail column, like 600 and above. I can do that, and I can keep labels that end up being bracket 0, 300, and it like programmatically shows you what is being grouped. You can also create numeric bins that then become bin 1, bin 2, bin 3, and you need to, in your own thinking, preserve what they map onto. And so I'll show you the labeled bin data. Again, echoing that you have a bin that's comprised by whatever the breakpoints were up above. And then I can do the same operation. Where is it? And get numeric bin data. So in this case, all of these entries fall into bin number 2. All right, so we're almost at the bottom for today. So some of the other things that are really important working with any data is manipulating strings. There's a statistic somewhere, but it's something along the lines of like 90% of data is unstructured text data. And so it follows that it's important to know how to work with this unstructured data, things like searching for data inside of data, replacing data inside of data. And so I'll walk you through a couple specific examples. So imagine you had a list of values, apples, app, and application, and you wanted to find app inside of it. So if I did that, I'll end up with 1, 2, and 3, because the result that I'm looking for, app, exists inside of entry 1, 2, and 3. I can do the same thing and actually return the values. So in this case, it'll show me the values that matched the thing I searched for. Okay. Now there's another version of this called grepl. It'll instead return logical values. This is helpful when you're trying to subset data, something we'll probably talk about more on Friday. Because what I'm trying to do here is to say which values are true, and then I can pass. Let's see, I guess I can just do this really now. And reproduce the results of the function above. I'm basically saying inside of this vector, apples, app, application, look for and give me the logical values where this is true, and then find me all of those values. So this is a long-winded and a long code way of saying the same thing as this function call up here. So they both fundamentally do the same thing. You're looking for or searching for data inside of data, specifically open-ended data. Stephen?
So I think another example that I found before, but I didn't just do this, is when your trials where it's an experiment and not right. So grep all the ones that have the word experiment next to it, and then eventually I grab all those rows and it's compiled to one big long list. So not to mainly go to my Excel and say ignore pilot or practice or whatever. That's how I use it.
Yeah, that's a great point. And Gabby, I think in your pipeline, we do something similar where we have grep to get the stimulus, like get what word people were shown, because it's like stimulus colon and then the word. So we're like looking for everything that comes after the word stimulus as an example. So then there's also G sub, which is helpful in its own way. You're looking to replace a value with another value inside of a list of values. So in this case, I want to replace the word apple with the word bananas in the vector apples and bananas. So I should end up with 2 apples, if I do that right. Sorry, 2 bananas. Same thing would follow with and error. So if I, like, for example, was writing out some log and I realized that my early version of the code was messed up, I can change to error by running the second line of code. And so it's basically the thing you want to replace, what you want to replace it with, and what are you looking inside of. So this is often helpful in a situation where, let me just create a fake example here. And so in this case, I'm looking for the stimuli colon string. And if I find it, I want to replace it with an empty string. And so in essence, what that does is that it removes the word stimuli in front of the word that I care about. So, you know, in one line of code, you can clean up a column that has multiple data inside of it. Yeah.
Would that be another way of solving the programming or the programming solution asked us before, like Alabama? Think of it AL, capital AL, Alabama, and just make them all one word. So you can look through that list and say, hey, place it all with this one word to keep it consistent.
You could, you know, in that situation, like what I was describing, I didn't explain the example fully, but imagine it was people said all 50 states. So then you'd have to like in that way of approaching it, you'd have to write out a case for each state. There's another way to do it, and we might get into it on Friday, I believe, but there's actually a package built into R called state that has a lot of these metadata.
I was trying to figure out that one. I'm like, I just find an Excel list of everything. Just read that one and do it that way.
It almost becomes that as the ideal solution. So continuing on, what I'll go over next is string search, but in a more sophisticated way. So imagine I was working with like genetic data and I had a bunch of A's and C's and G's and T's. I can look for certain patterns. So if I wanted to see every pattern of ACA and count them and count cases where they overlap, kind of like in a sliding window context. Oh, forgot to load the package. In this case, there are 3 instances of that. But now imagine I set up, let's do one more. There should be 4 instances. So you can count occurrences. You can also get the length of your strings. So this is important for the example that we were just chatting about with the states. If I wanted to look at the length of each entry that each person typed, I would say stringy underscore length for each person's response. If the answer is already 2, I can ignore those rows and I only need to apply the transformation to all the other rows that have, you know, string length greater than 2. I can also do something where I would look for duplicate letters, or sorry, create duplicate letters. So I'm basically saying, give me letters. So letters is a built-in object into R that actually contains all the letters. In this case, I'm saying, give me letters 1 through 5, A through E. And I want to duplicate by the sequence that's on the right. So for the first thing, give me one of those. For the second thing, give me two of those. For the third thing, give me three of those, onwards and upwards. So imagine I had changed this to 26. Should have 26 Z's if I did that right. So that's the general idea. With the duplication, I don't necessarily have a use case for that, although it's just cool to know that it exists. So you'd have to do that by hand. And then you can also do things like joining words. So in this case, I have a list of words, spam, bacon, sausage, spam, and then another one that's eggs and spam. And I can join them into a string if I wanted to have these multiple pieces of data rendered in one column for whatever reason. I'll leave that there. So in this case, I have two strings now as opposed to two vectors of values. I have one string that has spam, bacon, sausage, and spam. And just as simply as I did that, I can actually make the delimiter whatever I want it to be. So I can make it underscore delimited or colon delimited. So depending on what you're needing to do with the data, you might find that like a comma delimiter is actually problematic if the data you're working with has commas. So I always check that as like a assumption first, like, will this data ever have commas? If no, a comma separator is normally fine. If not, I should be using something else. Okay, continuing then, we have this operator that I've shown, I think so far a few times already. This is how to generate random data in R, at least one of the ways to do it. R has this operator called RNorm. There are other distributions that you can generate from, but I'll just stick with RNorm for today. And so I want a normal distribution with a mean of 500 observations with a mean of 300 and a standard deviation of 3. So let's go ahead and do that. Just generate a quick histogram of that to illustrate the fact that the mean is at 300. Most of the observations are there. It spreads out for 3 standard deviations. And so if I wanted to, I don't know, make the range tighter, I could. And we can just verify that that visualized appropriately. Now the values are, not wiggling too much beyond 300. Okay, so that was just to generate some data to show you that R has built-in mathematical operators like mean, SD, minimum, maximum. And so given that data that we just generated, I'll take the mean of it, which we knew should be 300 or around, we knew the standard deviation should be around 1, and it is. And we calculated the minimum and the maximum values from that. Now, if we wanted to know our quantiles, like where, let's say in one example, what value does 60% of our data fall below? We can use the quantile operator specifying either a single value like 0.6 or a vector of values if you wanted to know multiple breakpoints. So what I'll do is I'll create an example of each. So this would tell me that 60% of the data falls below 300.264. 95% of the data falls below 301.81, and 99% of the data falls below 302.33. But again, I can do this for multiple breakpoints at a given moment. So in this case, where does 1% of our data fall? Where does 99% of our data fall? And so this is helpful to do if you're looking at assumptions of distribution for your data. And that's the long way of doing it because you're typing out one mathematical operator at a time. This is something I only recently learned about, and it has changed how I approach thinking about data quality. So with one line of code from the skimmer package, skim R, I can actually generate a data quality report for a 1 variable data set or a 1,000 variable data set. It's all the same. So what I'll do here is just run through a skim report. Okay, I'll run through this one. This might be easier to see. So you essentially have a row for each column in the data. The first value is the type of the data. So you saw earlier on where we use class. This behind the scenes is calling class on each column to get its value type. Then you have the name of the variable, how many values are missing, how many are complete, how many So now if you're working with character data, it'll tell you the minimum number of characters within a cell, maximum number of characters that are empty, number of unique characters. And so this is helpful, again, if you're dealing with a lot of open-ended data and you want to get a rough sense, like what is the average length of response in like an open-ended feedback survey. And then that's all the character data, but if you have numeric data, it's further out to the right. So you have the mean, you have the SD, and then all those different breakpoints on the quantile distribution. And then at the end, you have a histogram built into the chart, which I think is the coolest thing in the world. You don't have to like write code to generate a histogram. Each row has it inherently built in. So if you, for example, we're about to meet with your advisor and you had, or they had questions about data quality, you can load your data set with one line, run a schema report with another line, and you have a data quality report ready to show. Whether it be in this tabular form or you can export it to a PDF and print that out, it's a really helpful technique to have in your back pocket. It basically means you're not writing one-off commands to check each of these assumptions for every variable in every data set. Okay, I think this is the last thing that we'll go over today, and this is essentially what I would call a data integrity functionality of R. So I sit on a technology and data management core of a really large grant for a longstanding aging study. And one of the things that I need to do is to make sure that the data that I share with someone is the same when they receive it. And it sounds silly, but imagine if they downloaded a file and they're thinking it's the latest release, but actually when we're creating the latest release, we dropped 2 in there and then deleted 1 after a couple hours. I want to make sure that they're working with the most recent. I can provide them what's called an MD5 hash. They can go in R, load the data, generate an MD5 hash of their data set, and it'll be the same if it's the same data. If one character moved out of place, if there's an extra space, an extra comma, an extra number, an extra row, the hash will be completely different. And so it ensures to me that the data that I'm sharing and the data that they're using is the same data. It sounds silly and it's easy to deal with in a lab, in a one-off lab where you're working with one other person. But when you're disseminating data that the public will now have for the rest of the end of time, you need to do things like this to make sure that everyone's working with the right data set and it didn't, for example, get corrupted when you uploaded it or get corrupted when they downloaded it. And so these hashes are so important. In one package that I developed a couple of years ago, it processes all the data that comes out of our mobile cognitive assessments. And the second it calculates anything, it takes a hash of the data set. So not only do you have the results you care about, the scores, you have a hash value. And so I can know and you can know that you're working with that data set that you took those values on and not one extra row or one less column. It is that data and that data only. And so it's to say it differently, it's as if I reduced an entire data object, whether it's a spreadsheet, an image, a video, to a set of numbers and letters. And so I'll just show you a couple really simple examples today. So it's part of a function or a package called digest. I can call digest on any string, any number, or any data object. And then I can use different algorithms to generate the hash. The most common ones are MD5 and SHA-256. MD5 has already been hacked from what I understand. So it's like something where if somebody wanted to do a malicious thing, they can open up the data set, edit it, and somehow force the hash to be what you had it. And so then the person ends up with corrupted data, but they think it's the right data set. SHA-256 is a hardened algorithm that I don't believe has yet been hacked. And so wouldn't hurt to generate one of each. I don't think we're in a situation where people are hacking our data, but if that's where our lives took us, like let's say one of us went off to work in national security or in intelligence, these things might actually be pretty important. So anyway, I'll call digest on A. I want to create one other version of this. So on A space, the hash becomes A62C2. On just A, it's 127E2. So just completely different values. And it echoes to me that I'm working with the right data. Now, this is just a string. So what does that matter? So maybe let's instead call digest on a whole data set. And so now this data quality report gave me this digest of BCA 90245. Let's just say, as an example, I came here and I just manipulated the data. Let's say I created, I don't know, column called fake, or it's column called data set with a value fake. I'll now come here and run digest again, and I got a completely different hash, C5. So I manipulated the data, and now the integrity snapshot hash is different. So that tells me that we're working with different data. So it's something that sounds a little edge casey right now, but the more you get involved with like data management of like multi-site data or large data sets, these things are really important because files do get corrupted when you're uploading and downloading. And so even though you think you uploaded and it worked fine, it might not have. And so it's important to like both download your data, check the hash, upload it, check the hash, maybe do that a couple times if you're working on a project where you think this makes sense. Stephen?
You say upload and download that to figure out to localize where the change may occur, because right now it's totally different, doesn't say where, but there's nothing out there right now that says, well, let me narrow your focus in, like.
Exactly. No, that's exactly right. I mean, there are tools. So the same way that I showed you in GitHub to take a diff of it, like two different commits, there are tools that would expose that difference in two data sets. I've used it before because it comes into bearing with like double entry of data. It almost exposed the holes of like, oh, these two people didn't agree on these columns or these rows. So there is a way to do that, actually, that focusing step. I'm just not remembering now how to do it.
Yeah, I didn't know if like in the Excel sheet to say, okay, let's do this for each tab. Okay, now let's then go ahead and go in this tab, let's go to this row or this one, and then we'll do a for loop and say, run through here, generate a thing. Oh crap, here's where it's different. Like, would that work? Like,
Yeah, that would work.
Okay.
I mean, there's probably a function called R to do what you just described, but yeah, exactly that. Like you can, the same way I took this hash on the entire data set, I can take it row wise, and that would probably more quickly localize the effect too. Well, thank you all for being with me. I know I kind of went over today quite a bit. Part of it was there was a lot of background, more background than I expected, that I wanted to spend more time on. So on Friday, the goal is to get through the Google Mobility data set and the survey data set. JSON is like a fun thing that we can handle in like 5 minutes. So my priority would be to get through the Google Mobility data set and the survey data. And then as time permits, we'll do more. But I'm fine and comfortable to stay a little bit longer any of the days like we did today. So if on Friday you all want to hang back and we want to have more discussion, I'm happy to do that too. Well, thank you everyone for making time to be here today, both on Zoom and in person. Recordings will be made available as soon as possible. My goal would be today, if not early tomorrow. And we'll just be doing more R stuff. I hope that maybe in the future we'd have a little bit more interactivity. Like, please come with questions and please let me know when things are confusing. I think we'll all get the most out of the workshop that way. So anyway, see you all Friday. Let me know if you have any questions, and also feel free to check out the textbook. A lot of what I went over today in words and visually and going through the GUI exists in that textbook. So that could be another resource to kind of complement what we went over today. With that, thank you, everyone. I'll mute and stop the recording.